So I'm going to continue part 2 from gravity. I'm going to go a little bit faster, hopefully. This is on page 5, the second half of page 5. So for gravity, we said that all objects on Earth are forced downwards by an acceleration called gravity. I'm using a black pen this time, a little bit easier to see. In theory, all objects are falling at the same acceleration. This is not always observed because of factors like wind resistance. Experiments without wind resistance have found that all objects fall at an acceleration of 9.8 meters per second. It's not technically 9.8 meters per second, it's like 9.806 or something like that. However, for the sake of this course, we're allowed to say that gravity is 10 meters per second squared, or meters per second, or 10 ms to the negative 2. Now, in reality, working engineers will always use 9.8 because 2% is a big deal, and we want to make sure that we're giving people the best value, but I just thought I'd mention that. Okay, what is the term for the force of gravity? I'll give you a clue. It starts with the letter W. Weight. Is the term for the force of gravity. In physics, weight and mass are not the same thing. No matter what the rest of the world, and no matter what your scales might say, we measure weight not in kilograms, we measure weight in newtons. Thank you very much. Your weight is a force measured, it's a force, and all forces are measured in newtons. And it changes depending on the gravity of the planet you are on. Your mass is measured in kilograms and will only change if you change your diet or do more exercise. Right? Now that's a thing from the Eureka videos. So your mass is constant, your weight depends on the gravity, and also other things like your acceleration in a rocket, for instance. Okay, the SI units are not based on Earth's gravity. So the mass of 1 kilogram, we said that weight is a force. What's Newton's law say about, Newton's second law says about force? Force is equal to what? Newton's second law says that force is equal to?
Mass times acceleration.
Excellent, thank you very much. So force is equal to mass times acceleration. Weight is equal to mass times, what's the acceleration?
What?
The acceleration due to Earth's gravity. Thank you. Okay, the SI units are not based on Earth's gravity. So if we have an object that has 1 kilogram, if it has a mass of 1 kilogram, if I have an object that has a mass of 1 kg, what will its weight be? What will its weight be? If it has a mass of 1 kilogram, it's 9.8 meters per second squared acceleration. 10. Yeah, 9.8 or 10. We're allowed to say 10 in this course. Okay, in the HSC course. You can't do that in physics, you can do that in engineering. Okay, now it's 10 newtons, not 10 kilonewtons. A lot of people, this is a really, really common mistake, a lot of people mix up and they write 10 kilonewtons. They say, well, there's a kg here, there's a k there needs to be a k there. That's not true. This is because the SI unit for mass is the kilogram and not the gram. I hate it, but that's the case. Right? We have a video on that where they talk about why that is the case.
How many newtons make up a kilonewton?
Okay. We're going to talk about how many newtons are in a kilonewton. How many newtons do you think? What does the K stand for? 1,000. So how many newtons are in a kilonewton?
1,000.
1,000 newtons. Okay. Now, it's useful for us to have an idea of something that weighs 1 newton. It has a weight of 1 newton on Earth's gravity. Now, as it happens, so anything that weighs has a mass of 100 grams weighs 1 newton on Earth. An example of that would be an apple. Apples have a mass of about 100 grams, and that's helpful because Newton is associated with apples. But I also have this to help you remember. So Newton, 1 kilogram times 1 meter per second squared is 1 newton. That's Newton. 1 kilonewton is about equal to 100 kilograms times Earth's gravity. So this guy, he weighs a kilonewton. Does that help you answer that question? 1 kilonewton is the mass of that guy. Yeah? 1 kilonewton is the weight of that guy.
So it's like
he's
equal
like
to
a
a
fat.
body weight.
A big guy. Yeah, 100 kilo footballer. Okay. So, the weight and 1 kilonewton weight is equal to the mass of the mass of a football player multiplied by gravity. The mass of a football player. Okay. When a football player with a weight of 1,000 newtons sits on a chair, he or she applies a total force of 1,000 newtons on the chair. If the chair has 4 legs, each leg takes 1/4 of the load. What's 1/4 of the load?
250.
250 newtons. What will happen if the legs can't support 250 newtons?
Right.
It'll break. So it's the job of engineers, now this is very similar to a line we saw earlier, it is the job of engineers to design structures and chairs that are strong enough to provide sufficient reaction force to push back up with enough strength so that they don't fail. It's the job of engineers to design stuff so it's strong enough that it can give a reaction without breaking. Okay. We're now going to talk about pressure, stress and strength. Okay. I do have an extra picture that I had to find. This one here.
So can we listen to that song again?
The weight versus mass song?
Yeah.
Not right now, but maybe later. I'm actually going to close this door because of the sound of the circular saw next door. Okay. Okay. Pressure, stress, and strength. The amount of force a material can withstand is not fixed. So we just said, can that chair hold 250 newtons? Well, it depends. An apple stalk and a tree trunk are made of more or less the same thing, but an apple stalk might fail when an apple's weight exceeds 1 newton, right? The stalk will cause the apple to fall, it will break off the stalk. Whereas a tree trunk can support 10,000 newtons. The difference is, what's the difference between an apple stalk and a tree trunk?
Tree trunk's thicker.
What's a more technical term, a mathematical term for that difference?
The mass.
Okay, so a
Volume is bigger.
one step back from volume. So that's what the
Area.
Area. The difference is the area. An apple stalk might have a cross-sectional area of only 1 millimeter squared, while a tree trunk will have an area that is 10,000 times greater. To calculate if a structure or a tree will be able to provide sufficient reaction force, enough strength to be able to prevent failure, you must divide the force by the area. Okay. Now, we don't use the word quotient very much in English, with the exception of maybe IQ. The quotient of a force of 1 newton divided by an area of 1 meter squared is the SI unit called the Pascal. I'm going to write that up here first. Actually, now I learned just recently that Pascal, the word, is written lowercase, but the unit that you write is written with a capital P because it's named after a person. Okay, so I want you to imagine if I had a piece of paper 1 meter squared in area. Yeah, so it's 1 meter by 1 meter. And then I put an apple on there. What did I say was the weight of an apple?
100 grams.
That's the mass of the apple. What's
1
the weight?
newton.
1 newton. 10 newtons.
1 newton. 1 newton. 1 newton, 1 apple, over an area of 1 meter squared. What do we call that? 1 newton divided by 1 meter squared is what is called what?
Pascal.
Pascal. Okay. Now, that's a really small amount, right? We often put more than 1 apple on the table. Yeah? So if we get, how many apples do you think we could put on an apple? Just in an order of magnitude. 10, 100, 1,000, a million, how many?
20.
More than 100, yeah?
Yeah.
What about more than, like if we stack them up before a table broke, could we put a box with 1,000 apples in there?
Yeah.
Okay, so we often deal with things that are 1,000,000 pascals. 1,000,000 pascals. Anything less than 1,000,000 pascals, we measure in thousands of pascals, called kilopascals. We usually refer to, okay, so anything less than 1,000,000 pascals is usually referred to as pressure. What are some things we measure that have pressure? We measure something pressures. So if you're watching the news, you might say at the end of the weather, they talk about air pressure. Yeah, the air pressure affects whether or not we have storms. They don't use kilopascals, they actually use something different, but we'll worry about that later. What's something else that you might have done? Something to do with cars that has pressure.
Pumping up the tyre.
Excellent, tyre pressure, exactly. Sometimes you might use PSI, that's an American unit, we don't use that. So we have tyre pressure. The other type of pressure we typically use,
Office.
now, the other type of pressure we use is we use soil pressure. Soil pressure. Okay, so we often talk about tyre pressure and soil pressure in engineering structures. Okay, moving along. Okay, in this subject we generally use materials that can withstand millions of pascals, and we use the term megapascals. Oh, sorry, we use the term stress. Now, for the stress, we can't use the letter S. We can't use the letter S, it's already taken, it's already used by too many other things. So we use a different letter. We use the Greek lowercase letter sigma. And the lowercase letter sigma, it looks like this. We use that Greek letter, sigma. There's another sigma, there's the capital letter sigma. We don't use that for stress. We use that to add stuff up. So, stress and the pressure are the same thing, but they're usually used at different times depending on how big the value is. When we're talking about stress, we're usually measuring things in megapascals. When we're talking about pressure, we're usually measuring things in kilopascals. Although it's not a base SI unit, we often work in megapascals. And it can be helpful to remember, I'm just going to write that in. It can be helpful to remember that 1 megapascal is equal to 1 Newton divided by 1 millimeter squared. Now I have a song about that, but we're not going to get to that one just yet. Anyway. Okay. A material's strength. A material's strength is also measured in pascals. How many newtons can it resist per square meter? An apple stalk might have a strength of 1 megapascal. Timber has a strength of, it can be anywhere from say 5 to 15 megapascals. Right? Steel has a strength of over 300 megapascals. The steel that we put in concrete has about 400 to 500 megapascals. Stainless steel can be nearly 2,000 megapascals, right? Definitely over 1,000 megapascals. Okay. It is the job of engineers to design structures of sufficient size to ensure the stress does not exceed the strength of the material to prevent failure. So what do engineers do? Well, they design stuff to be big enough so that the stress in the material is not so big that it's bigger than the material's strength. Because if there's more stress than the material's strength, the material collapses, it fails. Now, to help you remember that, I have a picture.
Yes.
So, does anyone know what this guy's name is?
Pascal.
Pascal, right? He's from
Tangled.
That's right, with Mandy Moore. Mandy Moore for me will always be the girl who said that's so funny. But anyway,
Is this a song?
nah, it's not a song.
Funny. That's so funny. Look how big that pancake is. That's
Anyway, I'm going to stop that now. Okay, so Pascal is equal to 1 Newton divided by 1 meter squared. Yeah, that's the definition of a Pascal. Stress and pressure are both measured in pascals. The term pressure is usually used when the value is small, less than 1 million, and it's written in kilopascals, and it's used for things like soil and tires. The term stressed is used when the value is bigger than 1 million pascals. Most of the time we use stress. Can you use those vectors? Okay. This really? The strength of materials is also measured in pascals. For example, steel, I would now write greater than 300 megapascals, concrete greater than 30 million pascals. Yeah, so concrete these days, I think 32 is now the lowest you could ever buy. Okay, so, we'll go to the next one. Vectors. Okay. All measurements can be classified as either vectors or scalars. Scalars have a size, or a scale, or a magnitude. For instance, temperature. Now, temperature can go up or down, but really when we're measuring the temperature goes up and down, it can never go left or right. Temperature can increase, or temperature can decrease, but it can't go 30 degrees to the north, 30 degrees south. It can't go 30 degrees up or to the left. It can only increase or decrease in its value. On the other hand, we also have vectors. Now, has anyone ever heard of a character called Vector?
Yeah.
Okay. So, where have you heard of Vector?
Oh, Despicable Me.
Well, okay, so in the movie Alita, there's also a character called Vector, but that's a different thing. So we'll focus on the one from Despicable Me.
Yes.
And hopefully they won't be...
Hey, go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh yeah!
Okay. So, vectors have both what? They have magnitude and... Direction and magnitude. Oh yeah, I hope you have the camera for that. Right? So, when we're comparing, we have vectors and scalars. Let's have a look at some examples. Vectors have both magnitude, size, and direction. Oh yeah. Gravity, for example, has a magnitude of 9.8 meters per second squared and a direction of... What's its direction? Gravity. Ready? I'll do a demonstration. Ready?
Down.
Okay.
Direction of...
Okay. So, gravity defines down. The force of gravity defines down. Gravity defines vertical. Defines down, defines vertical. Okay. Because gravity has a direction, we can deduce that all accelerations have a direction and are therefore vectors. Force is equal to mass multiplied by acceleration, so forces also have a direction and are also vectors. Weight, or it, is a force, so it is also a vector. What's the direction? So if I said that Paul Gallen has a mass of 100 kilograms, what is his weight?
10.
1 kilonewton down on Earth.
So wouldn't it be a newton because you bring 100 grams?
Okay, how did I do that? Sam's a little confused, so we're going to go through it. So, 100, so force equals, yeah?
Isn't it supposed to be kilograms? 100 kilograms equals 1.
Okay, so it's not just Sam. Force equals mass times acceleration. Weight equals mass times gravity, yeah? What's our mass? What's the mass we're talking about here?
Grams.
100
See, this is why we were confused.
I did say Paul Gallen. Okay, so I did say, you assume that Paul Gallen
Now we understand it.
Paul Gallen doesn't weigh as much as an apple. I was wrong. Everyone, I was wrong. I'm sorry about that. Okay, so 100 grams.
Sam was right.
Sam was right. 100 kilograms. 100 kilograms multiplied by 9.8 equals 980 newtons, which is very close to 1,000 newtons. Okay. We happy now?
Yes,
Yes.
we're happy.
Kai's happy.
Oh, you got Sam right.
Okay.
We don't even have Sam in the class.
How'd you get Sam, sir?
Sam Mustard.
Oh, sorry.
Okay. Two terms we often use in daily life are speed and distance. In physics, these are reserved only for absolute values without consideration to their direction, and they're scalars. When a runner runs a lap of the running track, she has covered a distance of 400 meters. So if you go to a running track, you might run 400 meters, but you're back where you started. Yeah, you're back at the starting line. So it would be impossible, if someone's back where they started, you can't really draw an arrow from where they started to where they finished. The arrow would have zero length. If she moved 100 meters to the north, she would now have a magnitude, 100 meters, and a direction of north. This value is where something is compared to where it started, where it ended to where it started, is called displacement. Similarly, where speed is equal to distance over time, we use another term called velocity. Has anyone ever heard of velocity? Yes. So it just comes from the French and Latin words for speed, and also it's very similar to the Spanish word for speed. One of these pictures here is about velocity. So velocité is the Spanish word for velocity, and in this example here I have another example, basically the same concept. Okay.
So are we going to listen to the song at any point in time? Yeah.
When I finish recording, I'm happy to do that. Okay. Similarly, where speed is equal... Okay, so velocity is the different... Okay, so what we're going to look at now is an example that compares those. Okay. If you do the Blackmore Sydney Marathon, you start at the Harbour Bridge and you finish at the Opera House. Now, you do all this running in between, right? How long is a marathon? Does anyone know?
42 Ks.
42.195 Ks, or 42,195 meters. Now, in the case of the Blackmore's Marathon, what's your displacement?
1,195 meters and 170 degrees south.
And direction, yeah? So that's the difference. This one is a scalar.
And that one is a vector.
Oh yeah. Okay,
Let's go.
so we'll go through some other examples like that later, but for the moment that will do.
I'm confused.
Okay. Someone's confused? Good opportunity to go through a
I
little bit
am
more.
so confused
Okay.
about all of this.
If we go through, if we're running, the distance is the whole distance they've travelled there. Yeah? This huge long distance. But when you finish the race, if we just measure how far you are from where you started, you've only gone this distance.
Oh, okay.
Yeah? They start the run here, they end the run there. Their distance is this huge distance, this huge thing here.
Oh,
They're just
But
like,
how far are they from where they started? How far have they been placed away from where they started? What is their displacement? They are only displaced about 1 kilometre, 1.5 kilometres.
but why do we need the 170 degrees south?
Because that's...
Because vectors have magnitude and direction.
Okay, got it.
Oh yeah. Now, I will say that there's a good argument to say, like, why do we care? Why do we need to know the difference? Well, the main reason is sometimes we have to add vectors. That's really the best answer. We have to add vectors together, and adding vectors together can give us more information than if we just use scalars. So sometimes we're going to add vectors. Like a good example people often use is if you have a boat that's traveling against the current. If you have a boat and the current, we need to be, or a plane traveling against a headwind, we need to be able to figure out what the end result of those two forces will be. That's where we use vectors. That's their purpose. Now, what we need to be able to do for our exam coming up is we need to be able to identify which are scalars and which are vectors. Time, we can never have a time go in any sort of direction. Time can only increase or decrease. So time is a scalar. Temperature is measured in, we talked about this earlier, what is temperature measured in? I'm going to write it here now, Kelvin. Kelvin. Now, the reason why we measure things in Kelvin, Kelvin is basically the same thing as Celsius plus 273. The reason we do that is so that we can get a more accurate measurement and we can get more accurate formulas. I'll talk more about that later, but for the moment we can just talk about Kelvin. Kelvin is the official unit. Distance, area, and volume are all scalars. On the other hand, displacement has direction. So displacement is a vector.
Then displacement is the one where they started, where they ended.
You got it. Exactly right.
Yes.
Speed and velocity are both measured in meters per second. Never in kilometers per hour. We always convert it to meters per second.
What's the difference between velocity and speed?
This one is a vector, so it has magnitude and
Distance.
direction. Oh yeah. Yeah, magnitude and direction. So velocity, so where we talk about a car, we say the car is going 100 kilometers per hour. If we're saying it's velocity, and I did just say before how we should always use meters per second. So if we said that a car was going at 30 meters per second,
Yeah.
if we're talking about the velocity, we need to say 30 meters per second north. 30 meters per second at 130 degrees. Yeah? Okay. Acceleration has a direction. In the case of gravity, what is the direction of acceleration?
Down.
Down. Okay.
Yes. We're getting it, sir.
Force and weight both have directions. Now, a force, if I'm pushing against an object, my force has a direction that way. But typically, as engineers, what the most common force that we're interested in is gravity, and gravity acts down.